Hello Science Junkie, I'm Sergio Hidalgo, an aerospace engineering student. Today I'm taking advantage of Spain's quarantine, and really almost the entire world is quarantined, to make a video in which I'm going to cover a pretty complex topic, so you might have to watch the video a couple of times to understand it, but what better occasion than this? When we all have a ton of time, we've got time to spare everywhere, but since it's something I had to explain, we're going to do it anyway. Today I'll explain it so you'll understand. What is aerospace engineering? Especially if you want to study aerospace engineering but aren't sure you'll enjoy it. This is your video because today I'll show you what you learn in aerospace engineering. They can complicate things or simplify them, but you'll have to face this regardless. So, well, let's get started with this video. By the way, if I'm wearing an orange sweatshirt with an orange background, well, I'll tell you why at the end of the video. So, well, let's get started with this video. If you've ever gone online to read about lift force, or maybe about the stability of airplanes, etc., you may have seen that it's said the lift force is applied at the center of pressure of the airfoil, so I'm going to explain what the center of pressure is so you can understand it. Forces in real life aren't applied at just one point, like on an airfoil. It's not that there's just one lift force pointing upward, but rather in reality, what happens is that there are infinite lift forces along the entire airfoil pushing upward. But can this system be simplified with just our airfoil and its forces?
Infinite lift.
Combined to form one large lift force. The point where that lift force is applied is the center of pressure. And for both systems to be exactly identical, you can only apply that lift force at one point, and that's the point where the moment created by that lift force is satisfied. For example, over the leading edge of the airfoil, which is what that moment is called in English. The rotation must match exactly the one generated for you. All the infinite lift forces along the airfoil with respect to the leading edge of the wing. So it's being fulfilled, the force is the same because we've said that the total lift force is the sum of all the infinite ones. Also, the moment from this force at a certain distance must equal the moment from all the infinite forces. And the point, the distance at which that is fulfilled, that's going to be the center of pressure. Well, but now we have a problem. As we increase the angle of attack, the center of pressure moves. Because the distribution of the infinite lift forces along the airfoil changes when you increase or decrease the angle of attack. And this is something that makes our lives incredibly complicated because if, for example, we start studying the stability of our airplane. By the way, if this were our airplane seen from the side and we zoomed in on the wing, we would have the center of gravity of the airplane, that is, the point around which it will rotate. Next is the lift force, applied at the center of pressure as mentioned. So, when you start analyzing this airplane at 0 degrees angle of attack, do you have the lift force that will make the nose pitch down? Perfect. However, the issue arises when we study this airplane's stability at a different angle of attack, such as 5 degrees. The lift force is going to increase because the angle of attack has increased, and we all know that the lift force increases when you increase the angle of attack, right? Perfect. Also, the center of pressure has shifted forward since, as we've seen, it moves when the angle of attack changes. Not only has the lift force increased, but the distance has changed too. That's why analyzing aircraft stability using the center of pressure is so complicated. But we are very fortunate. Nature, or the god of aerodynamics, gave us the aerodynamic center, making everything easier. It's amazing if we put the lift force at this aerodynamic center. Remember, as before, transforming one system into another similar one requires meeting two conditions. The first is that the force must be exactly the same, and the second is that the moment, meaning the rotation that force is creating, must be exactly the same. But if we see that the distance now to the beginning of the wing is different and that the moment is equal to the force times the distance, the force stays the same since we're just moving it forward, but how can the moment remain unchanged? Well, it's because we have to add an initial moment, which is what's known as the m0, in such a way that the lift force multiplied by the distance to the aerodynamic center plus the moment, the m0, has to be equal to the lift force multiplied by the distance to the center of pressure. The magic is that this aerodynamic center stays fixed even as the angle of attack changes. But not only that, the value of the moment, that is the m0, also doesn't change when you change the angle of attack. Here's an example to help you understand. Analyzing airplane stability using the aerodynamic center instead of the center of pressure gives us the center of gravity. Remember, the airplane rotates around the point where the lift force acts, called the aerodynamic center. And we have to add the moment, the m0, the one I mentioned to you. If we change the angle of attack, this moment stays the same and the aerodynamic center doesn't move. Only the lift force changes, increasing as the angle of attack increases, which makes sense. How is it that m0 stays constant? Even when the angle of attack changes, m0 doesn't change. It's one of the few things. People call it magic, but it's not. Does it have an explanation? I don't remember now. I'll explain in another video. I'm not going to discuss that now, or this would get crazy, but just remember it's real magic. Harry Potter, well, but I had forgotten to tell you the most important thing. And that is that the aerodynamic center for all airfoils, as long as they're thin airfoils, is located at a quarter of the chord. Draw a line from the start to the end of the airfoil, divide it into 4 parts, and the quarter point is where it falls. Exactly. The aerodynamic center is like magic, a gift from the god of aerodynamics. This is why when you explore stability topics, you'll find that all the books cover every aspect of stability. Always use the aerodynamic center instead of the center of pressure since it makes calculations much easier. And that's without the equations, because if I showed them, you'd see many things would disappear. m0 stays the same because the aerodynamic center doesn't move. I hope that explanation wasn't too complex because another similar one is next. Let's continue. I've talked to you many times about static stability, if you remember. In all the videos about stability that I've made, I've already made about 4 or 5. In fact, I've always said that for an airplane to be statically stable, the center of gravity has to be in front of the wings. That's not quite right. It was a good approximation, but I didn't want to complicate things, so I left it. So today you're going to discover the truth. Previously, I explained without considering the airplane's tail, but of course, this airplane has a tail too. But since I wanted to focus on the aerodynamic center, if you'll pardon the redundancy, I left the tail aside. But now, let's focus on the tail. Well now, if we look at the whole airplane and see how, for example, the wing is affecting the tail and the stability. There's something called pitching moment. It's actually quite silly. What makes my airplane rotate nose up minus what makes my airplane rotate nose down? That is the negative lift force generated by the tail multiplied by this distance. We put that as positive because it makes the nose go up minus the lift force of the wing multiplied by this distance because it makes the nose go down. The m0, the one I explained to you in the previous part, which if you notice is the equation I used in the flying wings video. What happens is that I said there it was equal to 0, of course, because if that's equal to 0, it means the plane is flying straight. But if, on the other hand, the value were, for example, positive, would it mean that the plane is rotating with its nose up? Or if it were negative, would it mean that the plane is rotating with its nose down? And why is this important? Well, you're about to see. Planes are designed so those values cancel out to 0, allowing straight flight. So if what we do is expand the equation a little bit, because, for example, the lift force, we know it's 1/2 of density times the velocity squared, times coefficient of lift, and times the wing area. The same applies to the tail, including its area and coefficient of lift. It's usually given a small apostrophe so that when you see the equation directly, you know it's referring to the tail. That means that absolutely all those variables come into play for the plane to be balanced or not. For example, when you design it, do you want it to fly straight at a 5-degree angle of attack? You realize that at 5 degrees it has a positive moment, so it can't fly at that angle. Since the nose keeps rising, what can you do? You'd adjust the equation so the nose goes up. Does it mean that the positive terms are greater than the negative terms? So, would you need to reduce the positive terms or increase the negative terms? Do you notice the velocity squared 1/2 and density there? Well, actually that doesn't really matter, because if I expanded the equation even more, which can be expanded further, moments can also be represented in another way, which I'm not going to show because I don't want to scare you, but just to tell you that if I expanded the moments further, could the m0 and m cancel out the 1/2 archo velocity squared? So that doesn't matter. Perfect. Now we have our trimmed airplane and it's flying straight. Everything's perfect. But if now suddenly a gust of wind hits our airplane from below, that's going to increase the angle of attack. Therefore, by increasing the angle of attack, everything has already shifted. Because your airplane is built to fly at a specific angle of attack, but if that changes suddenly, your plane is no longer trimmed. And that's why it's vital to study the pitching moment curve with respect to the angle of attack. We want to see how our straight and level airplane reacts if the angle of attack suddenly increases. We want to see if it will pitch up or down. Do you want to study this? Because what you always want is for your airplane to correct itself without the pilot doing absolutely anything. I mean, it's flying, a gust of wind hits it, moves it however, and you want it to return to its original position afterwards? That's called static stability, achieved by having a curve with a slope. Negative pitching moment relative to angle of attack. If a gust increases the angle of attack at 5 degrees, the pitching moment becomes negative. It would lower the nose to offset the increased angle of attack. That's why I explained it to you. The center of gravity is in front of the wing, which is the main point. So if the center of gravity is in front of the wing, the curve will have a negative slope, which is what we wanted. Why? Because when my plane is flying straight and a gust of wind hits it, increasing the angle of attack. As the wing's angle of attack increases, lift also increases. Therefore, the plane is going to climb, but since the lift force is increasing behind it, what's going to happen is this will lower the nose, allowing the plane to continue straight. However, if my plane had a positive slope, that would be like explaining it by saying the center of gravity was behind. That's not always true. I mentioned this at the start of the video, but explaining it this way makes it clearer. If a gust of wind hits it now, and the lift force on the wing increases the pitching moment, because it's positive, it would make the nose of the plane pitch up even more. Therefore, as it pitches up more, the angle of attack would increase even further. This would further increase lift. As lift force rises, we shift further right on the graph, so the pitching moment keeps increasing upward. Now we enter a loop where the plane's nose keeps rising until it stalls and falls. Well, when I refer to a gust of wind, I'm actually talking about any kind of disturbance. What could that be? It could be a gust of wind, for example. Even the pilot moving his hands abruptly. But if a plane is statically stable, that means that if the pilot pulls the controls, like pulls them abruptly, then lets go and puts them back in place. The plane has to correct itself without anything else happening. I mean, the pilot makes the plane go like this. He releases the controls and the plane self-corrects, returning to its original position. The concept is incredible. I hope you've reached this part of the video, Yankee, and understood it. If you like this video and want to see more videos like this, just let me know in the comments. Share it with your friends who must be bored these days during quarantine. If you really didn't understand it, I recommend you watch it again. Or even check out a book or something to try to get information from different sources. Maybe that way it'll stick in your head better. Because this had to be explained to me several times before I understood it, and I couldn't believe the thing about the aerodynamic center. Well, if you really liked it, give it a like. It doesn't cost you anything, and it really took me a lot of effort to make all those animations so the video could be understood. Oh, and to see if you've really made it to this part of the video, I've left a little airplane in the comments in the pinned comment. Just copy and paste it in the comments and in your comment, and that way I'll know you've made it to this part of the video and those who haven't made it this far in the video. Who aren't real science junkies will have no idea why people are posting little airplanes. Well, so why am I wearing this orange sweatshirt here? Well, because whoever tells me what this equation is, I'll put their comment in the next video. That's it, everyone. Science comes first, always.